morning, and thank you for coming. And I will start with a short video. Okay, so my work focused on the design and research of this new musical instrument, the Symbaline, as well as coming up with a new concept for a family of musical instruments consisting of sympathetic wineglasses. Probably you know at least one version of this quote, you don't let the weather just wait 2 minutes. Supposedly Mark Twain said that about New England. So this talk is going to be a lot like the weather in New England. I'll be bouncing a lot between music and design to engineering. So if at any moment it just bores you, just wait a couple of minutes and I'm gonna go back. Short structure, we will start with some inspiration sources and early prototypes of wineglass instruments. And then I will talk about the Symbaline, and I will focus on this specific mechanism of the Symbaline. And throughout the talk I will touch upon different subjects and thoughts within the design of musical instruments. And we will find out who this guy is. Okay, so designing musical instruments in academia is actually not uncommon. Probably a lot of you are familiar with Technion guitar by Mitzoran from MIT, which is like a hybrid acoustic electric guitar in which you can change the soundboard. And some other project, Hydrophone, which is really popular right now. They're having installations all over the world. It's like a water organ. And PeKA, which is really successful now, it's not a musical instrument, but it is intended for musical instruments. It's like an Arduino for audio. So the places where all of this happens are faculties which bring together design, music engineering, and computer sciences. And these are some of the prominent groups in MIT, of course, the Media Labs and CSAIL, Karma and Stanford, which is like a hybrid of music and engineering, and some groups in McGill and NIRCam, and some scientific societies where all of that is discussed and displayed. Okay, going back to my own work, my project actually started way before I was even a grad student. A very good friend of mine, Shai, was a cello player. Like most Israelis, he went to India. And when he came back, unlike most Israelis, he had a musical instrument with him, the sarangi. So the sarangi is a sympathetic strings instrument, and what it means that hopefully you can see we have really a lot of strings, dozens, way more than what we would anticipate on a cello sort of instrument. So before I explain what it is and how it works, I will take a more familiar and simple example of a guitar. How does a guitar work? Well, we first plug the string, and then I can ask a very naive question. When we plug a string of a guitar, how can the string know at what frequency or what tone it should produce? And I guess the physicists are familiar with that, a very naive answer to the question. This is the most classic example of like high school physics. Think of when you're on a swing, if you've been on a swing lately, you know how you can use your legs to increase the magnitude of the motion, but you will never change the frequency. With this locket, I can try to force it into vibrations or movements in other frequencies, but there's always one frequency in which I will get the largest motions with the minimal effort from my hand. So this frequency is called the natural frequency, and anything which vibrates or creates a sound or just moves around periodically will have a natural frequency. So that's true for children who swim, that's true for strings, and it will be true later on for wine glasses and water movements. And the natural frequency is determined by the mechanical properties of the system. With a swing, it's the length. With a string, it's the shape and thickness and density and so forth. All right, so I have a monochord here. It's a piece of wood with one string. And then when I pluck the string, okay, I get the natural frequency. And now we want to create sound. So I don't know if even the people at the back can hear this string, and that's on purpose. Sound is the vibration of particles. So right now in this room when I'm speaking, I'm using my vocal cords and my mouth to generate vibrations in the air molecules right here. And then these vibrations spread all the way to your ears. Which is, by the way, why in space no one can hear a scream, if you know this quote. It's not because of the helmets, it's because of the lack of air. So no air, no particles to vibrate. Okay, so in order to make sound, we need to vibrate particles. And there's a problem with strings, they are very, very thin. So there's not a lot of surface area. And when I pluck it, well, a few molecules move around, but not a lot. How can we make the sound louder? This is a very good analogy. You know how in water, if you want to splash water, you use this part of your hand with a lot of surface area, right? Sound is like that, and strings not having a lot of surface area, we not use a lot of air molecules. So I want to make this monochord louder. I will just place it on something big. So, but hopefully you can hear the difference. I'm not actually plucking any louder, I promise. It's just that the vibrations from the string are transmitted to the piece of wood and then onto the board. And the board, being like flexible and very large, creates a lot of air movement in your direction. So this is what we have with the guitar, only with a specific component responsible for that. It's called the soundboard. Connecting the string to the soundboard, there's a bridge. So vibrations flow from the string to the bridge and to the soundboard and create a sound. Now there's an interesting thing with waves, and the engineers know that. When a wave moves from one medium to the other, some of it is reflected back and moves back in the other direction. This is true for optics, it's true for transmission lines, and it's true in strings. In the guitar, this point of reflection transmission is going to occur at the bridge, the connection of the string to the guitar body. And this is actually a very useful feature when we design guitars and we want to control the sound. For instance, in flamenco guitars, the vibrations, the bridge is designed in a way that the movement of vibration is going to be very, very fast. And this is why flamenco guitars are these very loud, percussive, short tones. Now, classical guitars have the bridge area designed so the transmission of vibration is going to be much slower, and so the tone is softer and it's a bit longer in duration. All right, so we have sound and we have radiation. Now we're going to create a few tones. We're just going to shorten the strings of the guitar with a finger. And today I'm going to speak to the Western musical system. In Hebrew we use do, re, mi. It's actually Latin. These are names derived from this 8th century poem. The names correspond to the first syllables of the words in the poem. The American system consists of letters, and in engineering and acoustics we just use the frequency, or more accurately, the lowest frequency of each tone. And this is because tones contain more than one component. We're gonna speak on that later. Okay, so we have tones. We can use musical notation to write them, but in acoustics there's a different way to visualize sounds. It's called a spectrogram. Okay, so I hope this is intuitive. Going up, this is the pitch or the frequency. So high frequencies, low bass frequencies, and then in this direction it's the duration, long tones, short tones. What's nice about the spectrogram is that we can use it to visualize non-musical sounds. So hopefully you can see how the birds are like high frequency, the dog barks is low, and the siren goes up and down, and so forth. We can use the spectrogram to visualize sounds, and I would just mention that we can actually go the other way. This is a nice project by FX Twin, who is an electronic musician from the UK, and he actually created visuals in spectrogram and then reverse engineered the sounds. Okay, so now with all this knowledge, we can go back to the surrounding and understand how it works. On the surrounding, we have two sets of strings. On the top, we have three very large strings, like in a cello. And then on the bottom, there are over 30 sympathetic strings. And both of these groups are connected to the same bridge. Now, the way the instrument works is that a musician plays the top strings with a bow, like a cello, and then they vibrate. The vibration is transmitted to the bridge, like in the guitar. And now when the bridge vibrates, the vibrations are transmitted further to the sympathetic strings. So eventually we get these combined sounds of the main strings and the sympathetic strings without us having to directly excite the sympathetic strings. This is why they're called sympathetic. And this creates a very unique sonic effect, of reverberation, but it's very peculiar and it's instrument specific. And what's nice about it is that we get it without having to change the playing style. So we just play three strings, and then the rest sort of happens on its own. This is quite common in musical instruments, a lot of Indian examples, and then some classical guitars with sympathetic strings, and some modern examples. This is a contrabass with sympathetic strings. And we started examining the structure of these instruments. So strings transmitting vibrations to more strings, and we realized that physically speaking, this phenomenon of sympathetic vibrations may be implemented using other musical components. But in virtually all of the instruments that we could find, this part right here, the part receiving the vibrations, was always in strings. So we decided on our mission, we wanted to create a string instrument with some new sympathetic component. And we didn't know what. And we actually thought about strings with sympathetic chimes or maybe with sympathetic bells. Whichever, we knew that once we decide on a new sympathetic component, we would have to come up with a way to connect the strings to that new component. And we chose wineglasses. Before I go further, any quick questions? Okay, so very brief history of wineglass instruments. They actually started in Asia. The jaltarang is like a predecessor or set of ceramic balls tuned with water, and they played by striking. And then in the 18th century, the glass harp appeared in Europe, a set of tuned wineglasses played by drumming with a moistened finger. And he got to be slightly successful through the attention of Benjamin Franklin, and he came up with his own design. And the glass harmonica got to be really successful. Mozart, Beethoven wrote pieces for it. And this is where the evolution of these instruments pretty much ended. Now, we had our own reasons for choosing wineglasses. First, we knew that we could easily get wineglasses of a great variety, shapes, frequencies, materials, and so forth. And also, wineglasses take very little energy to put into sound production. All right, so we had our mission. We wanted to create a string sympathetic wineglass instrument, and our question was, how are you going to couple them? Seeing how in the sarangi all of the strings are just placed on the same bridge, we placed a wineglass on the bridge of a guitar, and that actually worked. So we created this experiment ring with a string going over a glass. The string was tuned to the glass frequency, and then when we plucked it, some of the vibration was transmitted into the glass, and the glass produced a sound. And that was an actual photo of the system and a sound sample. Alright, so we did manage to produce wineglass sounds, and we came up with some conceptual designs of new instruments based on this method. And our designs had a main problem. All of them felt really inconvenient as instruments. This is to scale. So this harp was going to be quite high and also quite wide. I think that I measured it, and I wouldn't have been able to reach the string on the far end. And the issue was with the degrees of freedom. Just by having to create this direct contact point between the string and the wine glass, we were left with not a lot of freedom to properly design the rest of the instrument. So we decided to come up with another way to connect string and wine glass in order to have some geometric distance between both of these components. And inspired by the string instrument, we created a bridge just from a flat piece of wood. It was inspired by the bridge of a violin. So we're connecting a string to a wine glass, we plug the string, and there's a contact point, and some of the vibration was transmitted into the glass, and the glass created a sound. Our bridges all had a problem. Quite a lot of the vibration was actually reflected back into the bridge, and it was lost. So we did manage to produce wine glass sounds, but they were very faint. So now a few slides of physics. The problem in this design was in mechanical impedance mismatch. So let's introduce mechanical impedance. It's a bit like in electricity, it's defined as force over velocity, it's frequency dependent. What it means is that if I try to shake any structure, but that's too heavy, but mechanical impedance is the amount in which the structure resists my vibrations. So high mechanical impedance, high resistance. And what happened to our system is that wine glasses have naturally low mechanical impedances, and our first bridges had high mechanical impedances, and so we have reflection, much like in transmission lines. Waves were going from the bridge to the glass, and they reflected. This animation was actually supposed to be faster. Some reflection. Now, the best way to transmit vibration is having the impedances identical, and so the wave just goes right through. And we knew that we have to redesign the bridge in order to match the impedances. Maybe before I go into the impedance designing, any questions so far? Okay, so we took an optimization algorithm to redesign the bridge. What it means is that this was our initial bridge. It had some very high impedance. Now what happens if I put a hole in the center of the bridge? The layout is now different, the impedance is different. So this is one way to change it. I can put two holes in the sides, and this is yet another different layout and another different impedance. Optimization means is that we're actually scanning through all of the possible bridges within these boundaries, and we're looking for the one with the most suitable impedance. So one slide of math, just to formulate that, we were looking on the bridge impedance, which is frequency dependent, and for simplicity, we took the average glass impedance over frequency, and we knew that this difference was way too large. It was frequency dependent, so we averaged it. And then we were looking for the bridge which minimizes the difference. And when we ran the algorithm, we got this. This was a new proposal for a bridge design. Put some solid wood at the edge, and then in the center, put this large hole. So we actually, when we simulated and fabricated this bridge, this is how it worked. Transmitted vibrations from the bridge to the wine glass. And we created, this was the system, and it produced sounds. Okay, so now based on that method, we could come up with newer designs which were indeed more compact and seemed to be more realistic. And that was a turning point in the research. The big question now was, are we actually going to build these instruments and who's going to play them? And the thing about musical instruments, as I guess a lot of you know, is that they take a really long time to study. The learning curve is really long to master an instrument. In the spirit of Indian music, I really like this quote. All right, so Ali Akbar Khan was one of the greatest sarod players of all times. He didn't specify how long you need to practice before you can upload videos to YouTube, but I guess it's a lot. And it wouldn't have been a practical choice for a PhD instrument to come up with something that it would take maybe 10 years until we got something to show. And then we started thinking about what defines the learning curve of instruments and how can we make it shorter. To illustrate, when we're speaking about instruments, so far, we mainly spoke about sound radiation, how they work and produce a sound. But what defines the learning curve is actually the user interface, the layout of the holes, buttons, strings, etc., anything that's got to do with interaction. Going back to our instruments, we realized that they may be acoustically well engineered, but they don't actually resemble anything which is familiar and popular. And so we anticipated really long learning curves. And once again, the problem was in the design. These mechanisms were too constrictive to actually design proper instruments. And we had to go back to our initial problem. Quick question so far? Okay. So we wanted to connect strings and wine glasses, and we tried some mechanical methods, and they didn't really work well. So how can we solve this problem differently? We will use electricity. How are we going to play a wine glass with electricity? We take a wine glass, place a small magnet on the surface, place an electromagnet in front of it, and then we connect it to a string instrument. Now the electromagnet creates a magnetic field, and the glass vibrates. This is what it looks like. Okay, so let's build a proper instrument. We take 12 glasses, we tune them by adding water to the 12 tones of the Western musical system. We take a string instrument, we split the signal, run it for a PC, amplify, and then send it to the electromagnetic coils. And at the center of the system, we have a PC, which is going to be useful later on to do some signal processing. Okay, so we actually achieved our goal. We had strings creating sounds of sympathetic wine glasses. That was the very first model. And it had one problem. It actually sounded really awful. Okay, so hopefully you do hear the wine glasses, but at the background there's a lot of buzzing and screeching noises. So to explain what's going on, again we're going back to the natural frequency. That's true for this locket and it's true for a wine glass. Any wine glass, depending on the mechanical properties, the material, the shape, will have one natural frequency in which it will vibrate and create a sound. Now when we try to excite a wine glass in that frequency, it will create a very nice ringing tone. What happens when you try to force vibrations in a non-natural frequency on a wine glass? It will produce these very awkward deformations, low amplitude, and they will create sort of like that, these very dry sounds. And that was the source of noise. So we were playing, for instance, Re on the guitar. The D was routed to all 12 glasses. Now up there we have one glass with a natural frequency corresponding to D, and that glass creates a nice sound. But then the other 11 glasses are excited with a non-natural frequency for them, and that creates a lot of 11 buzzing noises. Alright, so that was the problem, and we had to get rid of that. How are we going to do that? I'm going to demonstrate using two glasses. So we're going to use software filters. In front of the D glass, I'm going to put a D comb filter tuned to 587 Hz. When I play D on the guitar, the D goes through the comb, and most of it goes unfiltered. So it goes into the glass creates a nice sound. In front of the C glass, I'm going to put a C comb filter. When D goes through the C filter, most of it is attenuated, and then at the output there's nothing. So nothing goes into the glass and nothing creates a sound. These are two glasses. We're going to do that with all 12 glasses, the appropriate comb filters. We're now protecting each and every glass from any non-natural frequency. And after we did that, we got a slightly cleaner tone. Okay, another nice thing we can do with the PC right there is to use off-the-shelf audio effects. These are little pieces of software or plugins used frequently with like electric guitars and vocals and or recordings. We can use it on the signal for the wine glasses. So again, a sound example without any effects. couple of examples. Chorus is an audio effect consisting of taking a signal, splitting it, then introducing some frequency shift and combining. So we do that to the guitar signal before the wine glasses, and this is the sound that we get. And another example of flanger, slightly similar. It's taking a signal, splitting, introducing some time delay, and then combining. We now hear both the sound of the wine glasses with flanger and the guitar input, so the entire sympathetic system. Okay, so far I've only shown examples using a classical guitar, it's just convenient, but of course we can play the glasses with any amplified musical instrument. But we can also use sampled or virtual instruments. So what it means is that we simply have a bunch of sound files on the computer that were either recorded from actual physical instruments, that would be sampled instruments, or they were generated synthetically on the computer. That allows us to play the wine glasses with a lot of different input signals and sounds that we don't necessarily have physically. For instance, a sampled piano when played through a loudspeaker, well, it's an actual recording of a piano. But when we play that through the wine glasses, or a virtual marimba through loudspeakers, and then through the wine glasses, okay, so we tried a lot of different sampled instruments, and then we realized that we can come up with our own instruments, which we design specifically fitted for the acoustics of the wine glass. So we came up with some synthesized tones. If we play them through the loudspeaker, they sound very ordinary. This tone was intended as like a lead melody sound. So that's on the computer. When we send it through the wine glasses, hopefully it's got a little more ring to it. Another example of an instrument intended as pads or background music. So through loudspeaker, it sounds like a very generic synth. And through the wine glasses, okay, that was another turning point. That's a good place for quick questions if you have any. All right, so we had an instrument working, fully functional in the lab at the Technion, and now we realize that we want to make music. And if we want to take it outside the Technion and actually do something with it, there's a lot of other considerations that now we need to think of that were not relevant so far. Think of an actual scenario of us taking the instrument. No, actually not us, but a musician taking the instrument to a concert. So we now need to think of usability. The instrument is on stage, there's an audience, so we cannot have it fail. We need to think of durability and reliability, and suddenly simplicity is very important because it's going to be handled by a musician and not by a technical person. And it has to be mobile because I want to take it outside on a plane or on a car or on a truck, and many other considerations. So we had to come up with a new design, and with the guidance of Ezri, whom I don't see, Ezri, we created this new design based on sort of percussion instruments, really minimalistic aluminum stand where the electronics are hidden. And I'm gonna roll some photos of the fabrication process, and I will touch on something else in the meantime. So again, in this turning point, I got to ask myself a lot, at what point can I actually say that indeed a new musical instrument was created? There were a lot of milestones, publishing a paper, uploading a recording to YouTube, having a session with guest musicians. And surprisingly, one of the most important milestones was when we got to choose the name of the instrument. So for the name, I actually realized that technically speaking, the Symbaline doesn't generate sounds. It regenerates sounds of other instruments. And I came across this bird, lyrebird from Australia, called over there bulen bulen. And the lyrebird mimics the sounds of other birds or whatever sound it hears in the forest. So, to speak the lyrebird, bulen bulen, in that Aboriginal language, we misspelled and then it's seen for sympathetic, and that was our name. Questions? Okay, moving on to the last technical section. What's the deal with this mechanism? So let's hear the tone of an electric guitar. Alright. Hopefully you can hear and see in the spectrogram that the tone is really flat. Okay, it's very steady. Now vibrato is making a tone sound like this. So the frequencies are going up and down through the tone. And that's very important in music. Most musical instruments will have at least one method to produce vibrato. And up to that point, we had no such method for the Symbaline. This is the tone of the Symbaline. And the issue is that wineglasses have this natural frequency which is very sharp. And whatever we do, we can use DSP for some tone modulation or vibrato. But most of it, the wineglass simply resists. And so to create tone modulation, we realized we will actually have to change the wineglass itself. And we started looking around. This is a great inspiration source. Tremolo bars, a very simple mechanism for an electric guitar, creating vibrato. Alright, so we wanted to have something a bit more like that. And we realized that we can use the water inside the glasses to modulate the tone. And there's a nice example in an instrument called the Waterfall by Richard Waters. Alright, so what's going on is that at the bottom of the waterfall there's this hollow metal chamber with a little bit of water. And when the instrument is tilted, the water are sloshing inside and they change the natural frequency of the chamber and the tone is modulated. So we realized we may use that for our wineglasses. Two problems: the Symbaline is really heavy. We can't really tilt it, it's not practical. So we realized we have to come up with something stationary. And also, when we play the Symbaline, we were busy with the external controller, so we can really handle the wineglasses. So we had to come up with something automatic. Beyond that, we realized that we need to come up with something like a teaspoon that will automatically stir the water. In order to go ahead, we had to study some sloshing physics. So sloshing, which are these movements of liquids in glass, usually they are studied in really large vessels, fuel tanks and oil tanks, things like that. But one group studied sloshing in a cup of coffee. And their research question was actually, when you're walking around with a cup of coffee, suppose with no lid, what is the frequency in which you need to walk so the coffee will not spill? And they calculated that using the geometry of the glass, and they found that the natural frequency of sloshing is 3.6 hertz for an actual cup of coffee. Alright, so that's about this. We took that, we measured our wineglasses because they're slightly different with a concave base, and we came to the conclusion that in the wineglasses the natural frequency of sloshing is 3 hertz, and we were about to use this frequency. The reason was that in that specific natural frequency, we can get the highest vibrations, like the highest amplitudes, with the least energy. And we devised this mechanism based on a pendulum which sits inside the glass and steers the water. So it's hanging from above, and then at the bottom we have magnets responding to the magnetic field, and this is how it oscillates. And at the back we have a blade, so a large surface area to splash a lot of water. And we were using the existing coils as a source of energy. That was just convenient because the coils were already there. I mean, all of that was already fabricated. So The same coils used to drive the magnet will drive the pendulum. And we will use an extra signal. So we had a signal running the wine glasses, and now simultaneously we'll have an infrasound signal at 3 Hz to drive the pendulum. This is the sound we got. And a video example. So before activating the pendulum, and once we activate it, okay, let's investigate that. That's the tone of a wine glass excited by a classical guitar without the pendulum. It's a plot of the frequency over time, and there's slight modulation, but mostly it's stable. Now when we activate the pendulum, hopefully you can hear and see some profound modulation of the frequency. Another example using a flute or exciting the wine glass before modulation, and then with the pendulum in place. Alright, we still want to introduce some design changes to this mechanism. The power consumption is slightly too high. So as a sound sample, we took this single pendulum and we recorded individual tones on different wine glasses, and we created this example. This is what the Symbaline will sound like when we have the mechanisms running together. Alright, so the input here is of a classical guitar. Notice how profoundly different it sounds. Before I conclude, there's one last sort of abstract section. Any questions? Alright, so we now have an instrument, and actually most of the work is still ahead because now we need to make music. We actually have one scheduled concert, like a guided concert in a guitar festival in La Mans, France. But beyond that, we're really curious to know what's going to happen with the Symbaline musically. And the point we realize is that it's impossible to know what's going to happen with an instrument just by inventing it. And I want to illustrate that with a familiar example. Thinking of a saxophone, I can think that most people would think of jazz and probably the United States and probably the 40s. The thing is that the saxophone wasn't actually invented for any of that. It wasn't invented as a jazz instrument. So that's a little quiz. The saxophone was invented in
Germany.
In the world. Okay, it was invented in Paris. What year?
19th century.
The saxophone was invented in 1846. Who was the inventor? That one is easy. Sax. So that's the guy of the sax. And one of the early uses for the saxophone was in a military marching band. So that's really unexpected. And encouraging, because you cannot really know what's going to happen with an instrument and what the musical potential is until you just set it out to the world. On the other hand, we do want to know if an idea for a musical instrument is any good and is it worth pursuing without waiting a century. So how can we know that? I came to realize that a lot of very innovative instruments are actually small evolutionary steps from other instruments that were already really well established. The saxophone, to a degree, is sort of a clarinet made from brass, trumpet material, with some fluid acoustics. And this is not a coincidence. Out of sax played clarinet and the flute. So we don't know what's going to happen with the Symbaline and if it's going to be successful. But whatever success or whatever interest we already generate, I tend to attribute it to the fact that our vision was really down to earth to start with. Because the Symbaline is essentially us saying, sympathetic string instruments are nice, people like them, at least in India they do. Wineglass instruments have some potential. We can bring them together using existing technologies and then make it accessible using familiar interfaces. Few open questions. We do contemplate creating our own resonators instead of ready-made wine glasses. There's advantages and disadvantages to that. But mainly the big question is how musicians and audience would want to use the Symbaline. And this is out of our hands. The only thing we can do is investigate that, and then accordingly we may have to introduce some changes in different features, different sonic features, and so forth, based on what the musicians will decide. In a larger context, and this is generally speaking about this discipline of musical instrument research within academia. In musical instruments, there seems to be quite often a gap between the people who know how to make them to the people who know why to make them. And this actually exists in a lot of disciplines. And to me, the role of academia in this world of musical instruments is to serve as a bridge between these two groups of people and assist the creation of new musical instruments that are both technologically advanced, but also musically meaningful and desired and useful. All right, so recapping, we created a new family of musical instruments with sympathetic wine glasses. We started off with some mechanical prototypes, and then we created the Symbaline and investigated it in many different ways, and we came up with a sloshing mechanism. Some acknowledgments. I'm sure you all realize that a project of this magnitude is never actually done by a single person, and that's true for the Symbaline as well. There's so many people who help in so many different ways, and like loaning equipment and giving advice and anything. So I'm not actually going to name names, just for my family and my partner. And I also really want to acknowledge the faculties. So both faculties, architecture and design and engineering, my supervisors, Yoav, who is here, Noam, who's abroad, Nomi and Ezri, who supported this project right from the start. And I know this is a somewhat unorthodox research, so it probably took a lot of foresight to support, so thank you for that. And thank you all for listening.
Questions? Yes.
You design new instruments, that all of them are limited by the mechanical oscillating properties of matter, various matters. In synthetic music, you can free yourself of them. You can generate something that is like the blending of two of your instruments, and or get the frequencies out of harmonic relationships. So have all the freedom. Why play and limit yourself to all these mechanical toys?
Yeah, we discussed that a lot. So, indeed, in computer music, you're limitless. You can do anything. This is very subjective, but for a lot of people, the experience is what counts. So, music is more than just like auditory signals coming into your ears. Again, this is subjective. So, for some people, knowing that the instrument is physical, it exists, you can see it, you can touch it, creates a sensation that is, well, this is what creates the enjoyment of music. And for other people, it's not. And I know, people from all of these disciplines, like totally theoretical computer music, like just a laptop and keyboard, and some people like acoustic instruments, absolutely subjective. From, I guess that from a physical point of view, you're mostly right. Besides a few details, you should come later and try to listen to this instrument. The radiation pattern is actually very complex because you have sound coming out from a lot of different places. That's very sort of confusing, and I find it to be enjoyable, of course, but you will not get that with a computer. Okay, so that's true for a lot of instruments. A piano, which is huge. When you sit in a room listening to a piano, physically speaking, it doesn't it sounds like a piano coming out of a speaker. So there are some physical differences, but I would say that like 95% of the difference is subjective, just what a person has.
Yes.
How did you do the analysis, measurement of vibrations?
The vibration
vibration patterns of the bridges and all these things.
The vibration pattern or what? Sorry.
Of your the bridge.
Oh,
Other
okay.
thing you
So-
design something, did you verify by measurement?
Yeah, we use COMSOL multiphysics for simulations, and then our measurements were acoustic. We just recorded tones and analyzed.
And just with the acoustic. The acoustic analysis of the vibration, but you didn't check the actual vibrational modes of the.
True. So we didn't do interferometry and we didn't do vibrometry. That would have been a nice.
Yes.
Well, if I want to learn how to build something like this, is there like a paper that you published?
There are several, yes.
Yeah.
So
Maybe I didn't see the bottom line.
yeah, we have 3 publications. The first is on the acoustic part, the optimization and mechanical instruments. Another paper on the Symbaline and another paper on the pendulum. So just approach me later and
No
send you
problem.
the papers.
Thanks.
Okay, one last question. Yes. Guy.
So could you couple the strings to the,
Yeah, we're gonna have a session now. So like 5 minutes break and then you can come up and play.
unfortunately I have to teach. That's just the question.
We can hear.
The question
Yeah,
is
but
just, you can couple also the strings to the resonant mode of the glasses by resonant coupling without all the mechanics and the electromagnets, can't you? I mean, if it's tuned to the natural frequency of the string, it will couple if you play close enough, wouldn't it?
Like acoustically coupling through the air.
Yes.
I didn't have much success with that. I mean, you will get something that probably it's not going to be loud enough.
Not loud enough, but
Yeah, or I'm not even sure if it's audible. It depends on the glass, on the
you
guitar.
just play between 2 guitars. You
So
play a
let's
string in one
taking a
guitar,
guitar,
you couple to
standing in
the
front
other.
of the glasses and playing. It will produce something. I don't know if you can control it well, but it's a nice direction.
יש פה מוזיקה.
זה בא מהכוסות יין עכשיו? אז אולי שהוא יש שם רחוק שאפשר יהיה להחליט מה בספור.
זה משחק, אני צריך לשמוע בעצמו.
כולנו עובדות כמה שנייה לידם. יש סרטים שהוא במיוחד.
אני חושב שחלק מהכוסות התאבדו.
זה נשמע טוב.
זה בעצם מילימטר.
זה לא נראה שזה המקור על הסאונד.
זה קצת קריפי כזה.
זאת
לגמרי.
קצת
חזק.
אייטם.
כמו,
בוא נעשה את זה עוד פעם.
קריאה
תסתכלו על הכוס בכיוון של מצדה.
כן. ממש כזה.
שזה רזוננס.
כן.
כן.
וואי, איזה יופי.
עכשיו יש גם נון-ליניאריטי, אז אנחנו גם לא תמיד יודעים מה לצפות.
יש
חלק
קאפינג
מהקסם.
בין הכוסות?
לא, לא. מסתכל, נגיד על הכוס, עזוב, כוס גדולה. אני מכניס פיור טון ממה שאמור לקרות. עכשיו, אני רואה קצת רזוננס, אם התדר רחוק, היא בקושי מגיבה. יש סאונד אבל היא בקושי מגיבה. גבוה מדי, נמוך מדי. התדר הנכון, זה האזור. עכשיו אני רוצה למצוא בדיוק. נגיד אני כרגע מניח שבגלל שכיוונתי את זה לפני כמה שעות, טיפה מים התאדו, שזה אומר שאני גבוה מדי. אני מעלה טיפה את הטון, שזה די מדויק. אז נגיד זה פחות או יותר התדר. נגיד שהייתי רוצה לעשות אותו טיפה יותר נמוך, עכשיו זה 466, אני רוצה להוריד אותו ל-460. אני צריך להוסיף מים, אני פשוט הולך להוסיף מים עד שאני הולך לראות את הרזוננס חוזר. אוקיי? אז מה שהוספתי עכשיו זה היה 6 הרץ. וככה בעצם אני יודע איך אני פוגע בתדר.